Have you ever wondered how your computer can instantly find a photo, play a video, let you chat with a friend, all at once? It feels like magic, but it is not. It is the result of a carefully designed plan called system architecture. This architecture is the master blueprint. It dictates how every component works together in harmony. Understanding this blueprint isn't just for engineers, it shapes our lives, from the smartphone in your pocket to vast cloud networks to the AI systems of the future. System architecture is about organization and communication. Imagine building a car without a plan, an engine, wheels, a steering wheel, but no idea how they connect. Likewise, a computer has a CPU, memory, storage, and other parts. Architecture defines the pathways and rules so they can talk efficiently. This chapter will demystify core system architecture concepts. So, yeah, let's get into it. The Central Processing Unit, or CPU, is rightly called the brain of the computer. It is the component where the vast majority of calculations and logical decisions happen. At its most basic level, the CPU's job is to execute a sequence of stored instructions that make up a computer program. Each instruction is a very simple command, such as adding two numbers, moving a piece of data from one location to another, making a decision based on a certain condition. The CPU fetches an instruction from memory, decodes it, executes the command, moves on to the next one, repeating this cycle billions of times every second. To perform its tasks faster, the CPU doesn't just work on one instruction from start to finish. Modern processors use a clever technique called pipelining. Think of it like an assembly line in a factory. An instruction is broken down into smaller steps: fetching, decoding, executing, writing the result back. Pipelining lets the CPU work on different stages of multiple instructions at the same time, one being executed, the next being decoded, the one after that being fetched. This overlap dramatically increases instructions completed per period without needing a faster clock speed. Another critical feature for speed is the CPU cache. Cache is a small, extremely fast memory built into or very close to the CPU. It acts as a high-speed buffer between the CPU and the much slower RAM. The cache stores copies of data and instructions the CPU recently used or will likely need soon. When the CPU needs data, it checks the cache first. If the data is there, a cache hit, it's retrieved almost instantly. That avoids the long delay of fetching from RAM, reducing wait time, and keeping the pipeline full. Sometimes an external device or a software event needs the CPU's immediate attention. This is handled by an interrupt. An interrupt is a signal that temporarily stops the CPU's current task for something more urgent. For example, when you press a key on your keyboard, the keyboard controller sends an interrupt signal. The CPU pauses its work, runs a special piece of code to process the keystroke, then resumes its original task. This lets the computer respond to real-time events, mouse movements, network data arrivals, without constantly polling every device. Cool. For the CPU to perform its work, it needs a place to hold the instructions and data it is actively using. This temporary workspace is called Random Access Memory, or RAM. Think of RAM as a workbench. It's where you lay out what you need for the project you're working on. When you launch a program, its code and data are loaded from long-term storage into RAM. The CPU can then access this information directly and very quickly. However, RAM is volatile, requiring constant power to maintain its information. Once the computer is turned off, everything in RAM is lost, like clearing your workbench after a project. We also need a place to keep files, applications, and the operating system permanently. This is the role of storage. Unlike RAM, storage is non-volatile. It retains data even when power is off. The two most common types of storage are hard disk drive, solid-state drive. Your photos, documents, and games reside in storage until you decide to open them. The relationship between RAM and storage is crucial for system performance. Because storage is much slower than RAM, data constantly flows between the two. When you double-click an application, the OS finds its files in storage and copies them into RAM. The CPU then works with the data in RAM. When you save, the updated version is copied back to storage. If RAM fills up, the system starts swapping with the much slower drive, which can make the computer feel sluggish and unresponsive. The instruction set architecture, or ISA, is the fundamental language the CPU understands. It is the vocabulary of commands the hardware is built to execute. Every program, no matter how complex, is ultimately translated into a series of these simple instructions. For example, A program, written in a high-level language like Python or Java, must be compiled or interpreted into the CPU's ISA, such as x86 for most desktops, or ARM for most smartphones. This is why you can't run a program compiled for a Windows PC on a Mac without translation, or a version compiled for the Mac's architecture. So, yeah, that's how the workspace and the library work together to keep your computer running. Section 4. Connecting the pieces, buses, and input/output, I/O. Section 4. Connecting the pieces, buses, and input/output, I/O. Section 4. Connecting the pieces, buses, and input/output, I/O. A computer is a collection of specialized components that must constantly communicate. These communications happen over electrical pathways known as buses. A bus is essentially a data highway connecting major parts of the system, such as the CPU, memory, and storage devices. Like a real highway system, there are different buses for different purposes. For instance, the system bus, or front-side bus, links the CPU and the RAM at high speed. A peripheral bus like USB connects slower external devices like keyboards, mice, and printers to the main system. The speed and width of a bus are critical to performance. Bus width is how much data can move at once, like the number of lanes. A 64-bit bus moves 64 bits simultaneously, making it faster than a 32-bit bus. Bus speed, measured in megahertz, is transfers per second. If the bus is too slow, it becomes a bottleneck. Even the fastest CPU must wait if it can't get data to and from memory or devices quickly, just like a sports car in a traffic jam. Section 5. The conductor. How the operating system manages it all. The operating system, or OS, is the master software that brings the hardware to life. It acts as a central manager and a conductor, coordinating hardware and software so they work harmoniously. When you turn on your computer, the OS is the first major program to load. It takes control of the CPU, memory, storage, and all connected devices. It provides a stable, consistent environment for applications, so developers don't need to handle low-level device details. One critical role is process management. The OS shares CPU time among many programs, switching so quickly it appears they run simultaneously. It also manages RAM, tracking what's in use and what's free, allocating memory to new apps and reclaiming it when they close. Finally, the OS manages all files and devices. It provides a file system for storing and retrieving data from your hard drive or SSD. This lets you create folders, save files with names, and navigate storage logically. The OS controls input and output devices via drivers. When an app wants to print, it sends a request to the OS, which uses the printer driver to complete the task. By acting as intermediary, the OS abstracts hardware complexity. Section 6. The rise of intelligent machines. AI hardware and parallelism. AI has placed unprecedented demands on architecture, leading to highly specialized hardware. CPUs are generalists, great at sequential tasks, but many AI workloads are massively parallel. GPUs have thousands of simpler cores, ideal for SciMD and neural nets. They run huge matrix operations in parallel, slashing training time. Companies then built even more specialized AI accelerators, Google's Tensor Processing Unit, TPU. TPUs are ASICs designed for tensor computations. By removing general-purpose parts, they pack more compute per watt. These accelerators power large-scale AI services. Real-time language translation, image recognition in the cloud. Specialized parallel hardware now defines modern data centers. Cloud providers offer powerful GPU instances, and TPU instances rentable by the hour. Developers can train small models on a single GPU, then scale to clusters of hundreds or thousands. Architecture evolved to power intelligent applications at scale. Section 7. Conclusion. Assembling the puzzle and your next steps. In this journey, we saw how the CPU, our computer's brain, executes instructions, boosted by cache and pipelining. Work happens fast in RAM's temporary space, while your files live in slower, permanent storage. Digital highways, buses, link components, and I/O connects the machine to the outside world. Overseeing everything, the operating system conducts resources so apps run smoothly. And as AI rises, parallel hardware like GPUs and TPUs crunch huge workloads at once. Understand these pieces, and the tech around you suddenly makes sense and feels yours to master.